Hello everybody, welcome to the first lecture in Unit 1. And Unit 1 discusses primarily about crystal structures. So before doing that, I want to give a brief introduction on some of the quantum mechanical concepts and describe the atomic structure and talk a little bit about the quantum numbers and interatomic forces, and a brief overview of the primary bonding that exists in atoms. Okay. So the Bohr model of the atom is well known to all of you, I believe, and essentially it talks about the atom having a nucleus, and it is surrounded by these electrons that are orbiting this nucleus in this orbitals, and these electrons we know are negatively charged, and the nucleus has protons and neutrons, and the protons are positively charged. Okay. So, however, we know that this model that we use of Bohr is quite limited, right? And actually, if you take a look at the quantum mechanical picture, we don't have the electron that is localized anywhere, right? So we have a picture something like this, where you have the nucleus but the electron is much more delocalized, right? And when we are trying to locate this electron in our atom, basically we try to find the probability density of where the electron is located. Okay, so we cannot know for certain, right, where the electron will be located. Okay, and in this process, what we do is we use the quantum numbers. There are 4 quantum numbers, as you might know: the principal quantum number, the azimuthal number L, and the magnetic quantum number, and the spin quantum number, right? So these 4 quantum numbers is used to describe an electron, and where the electron might be located and what energy it might possess. Okay, so this is a unique signature, and it describes each and every electron, and we can characterize each and every electron in the system by labeling them with these quantum numbers, right? And essentially, once we assign these values, essentially what you're doing is you're putting some constraints on the system, right? So then we can look at a system where you have multiple electrons in an atom, and then we can ask which orbitals are filled and which orbitals will be empty, right? So then we use some principles like the Aufbau principle, which tells you which shells should be filled, and so we start with the lowest available energy state, and then we start filling them, and then you can have the Maddeling's rule, and so the energy ordering is from lower value of n plus L to the largest value of n plus L. So this is how the picture looks like. If you are trying to fill many electrons in an atom, you start with the 1s shell, and then you go to 2s, 2p, 3s, and so forth, right? So now we want to ask is what happens when these atoms they come together. Okay, so why do these atoms they actually form crystals, and what is the mechanism of this formation, right? So we want to understand when now these atoms they will come close to another atom, how will they bind with each other? Okay, so will the electrons be responsible, right? And if they bind with other atoms, will the quantum mechanical properties change? Okay, and so you can have a scenario here which talks about interatomic bonding. So you can see if you have atoms that are very isolated and far apart from each other, then they will have no interaction among them. Okay, but as these atoms they start uh, moving closer to each other, they will start exerting some forces on each other. Okay, and this force, it can be an attractive force that can result because of some bonding that might occur between these atoms, and at the same time these atoms they have electrons which are negatively charged. So as these atoms they come close to each other, so these electrons, this cloud will start overlapping, and they will actually cause a repulsive force. so eventually what will happen is, when these two atoms, they are coming close to each other, essentially you will have a certain position where you have this minimum potential energy that will develop, and this is your equilibrium position, where the atomic separation between these atoms is ideal. Okay, and so if you look further as to what is actually going on, so this minimum value where this potential is minimum, right, so that is given by this value du by dr. So as you can see in this curve, that minima is 0, right. So this corresponds to your energy that is required for your bonding. Okay, so if this value here is a very large value, right, so then we can conclude that the bonding energy between the atoms is very large, right, and this can signify to us that if this kind of bonding is happening, and this is the potential energy curve that is getting resulted, so you will have a solid that will have a very high melting temperature. Okay, however, if you have the value of this energy function here, which is low, then that would essentially mean that whatever the bonding is happening is weak, and so it will result in a formation of a liquid or possibly a gas. Okay, additionally, this interatomic bonding curve, the slope that develops because of this attractive and repulsive forces, can tell you whether the material is going to be a very stiff material. So if you have a very stiff and sharp slope, then it is a very stiff material, and if you have a very shallow slope that occurs, then you can conclude that this material will be very flexible. So that is the kind of bonding that will exist in the material. Okay. So again, if we talk about bonding, then we have different types of bonding that you might be familiar with. So we have ionic bonding, and in ionic bonding you have basically a metal that might be in a favorable situation to give away one of the electrons to the neighboring atom, and in doing so, both of these atoms, they attain basically stable configuration, and so that is what they prefer to do, and there will be a bond that will be formed, and this is basically a non-directional bond that will be formed, and these bonding energies are quite high in ionic bonding, as you can see from here. Okay, and the other type of bonding that you might get is covalent bonding, and in covalent bonding, basically there is no loss of the electrons, but there is basically sharing of the electrons that happens between the two atoms, right. So now we are talking about a directional bond that can happen, right. The third type that is very common is the metallic bond, right. So you have these electrons that are basically delocalized, that means they can roam around in your solid, and essentially that gives the metallic character to the material. Okay. Additionally, when you talk about bonding, especially in inert gas atoms, you might encounter something called Vander Waals interaction. And essentially, if you look at this picture here, you have the atom which is positively charged, and it is surrounded by the negatively charged electron. And when such atoms, they come close to each other, there can be polarization of the charges, and this might lead to a slight attractive potential that might develop between these two atoms. Okay, and these van der Waals interactions are generally weak compared to the other bonds, and so they are reflected by these low melting points that exist for these stable atoms. Okay, and apart from that, when you talk about molecules, you might encounter something called hydrogen bonding, and essentially this is the dipole interaction between molecules, right. So here you can see all these hydrogen and oxygen and nitrogen, these elements, they have the electronegativity with them, and so the hydrogen is slightly positive as compared to the oxygen, and so it might have this attractive hydrogen bond that might form, and so the molecule might reorient itself accordingly. And so these all these molecules, when they come close to each other, they might rearrange themselves in a particular fashion. Okay, again, when we look at these atoms, essentially, we have to keep in mind that they are governed by these rules of quantum mechanics. And when we talk about the crystal structures in the next class, we understand where they come from and how they actually form bonds and rearrange themselves in a lattice structure.